Hello, I'm going to be doing week 7B homework fluids. This is my Jedi lesson. For the first question, I want to do question 1. A mercury barometer reads 750.0 millimeters on the roof of a building and 760 millimeters on the ground. Assuming a constant value of 1.29 kilograms per meter cubed for the density of air, determine the height of the building. Okay, so in this situation, let's just check out what was given. Or I guess we could draw it first. Mercury barometer is 750 and on the roof of a building and 760 on the ground. So this would be the building. And it'd be 750 up here due to the barometer. And 760 down here. SI units being millimeters. And the density of the air would be 1.29 kilograms per meter cubed, with the SI units being kilograms per meter cubed. So now we can write what was given to us. What was given to us was the pressure of the ground, pressure G, which is 760, and then the pressure of the roof. Sorry for the letters. It's pretty hard drawing with this mouse, but 750. And the density of the air, which is P is equal to 1.29 kilograms per meters cubed. Ooh, that's an ugly cube. Cubed. For this specific problem, we want to use the pressure difference between the top and the bottom. So let's write it up here. The pressure difference. The pressure difference would be 760 minus 750, which is obviously going to equal 10 millimeters. And we're going to use the 760 because, okay, we can convert 760 millimeter into 101.325 pascals in this situation. And since we know the pascals, because we can't use this, right? We can't use this SI unit. We want to use pascals, right? For the hydrostatic pressure equation, we're going to be using pascals. And if we do the equation here, it's going to be 10.0 times, which is the change in P, 101.325 pascals over 760, which is going to get us to equal 1333 pascals. So 1333 pascals. And after we get this number right here, we want to use the hydrostatic pressure equation, which I'll write it down here, PGH. And we want to rearrange this because we want to be solving for height in this situation. So if we rearrange this, what we're going to do is we're going to get H is equal to change in P over PG. Boom. That's what we got. And all we got to do from here is just plug in. So H is equal to 1333 pascals, because that is what we solved for here, over 1.29, which is the density of the air right here. And it's also, oops, let me do the equal here. Get tripped up. Thought it was a negative for a second. And 9.81, because that's the gravity. 9.81. And what we end up with is going to be 105.3 meters, which is just equal to 105 meters. This would be the final answer in this situation. This is meters per second squared. So SI units for the gravity. So 105 meters. Boom. And that's going to be question 1. Now, for my second question, I want to do question 14. The density of ice is 917 kilograms per meter cubed. And the excuse me. And the density of seawater is 1025 kilograms per meter cubed. A swimming polar bear climbs onto a piece of floating ice that has a volume of 4.37 meters cubed. What is the weight of the heaviest bear that the ice can support without sinking completely beneath the water? So, we're going to write out what was given. Just right off the rip, we want to write what we have so we know what we can use. So, we were given the density of the ice, which is 917 kilograms per meter cubed. We were also given the density of the water, which is P water is equal to 1025 kilograms per meter cubed. We were also given the volume. The SI units for the density is kilograms per meter cubed. The SI units for this volume here is going to be, well, it's going to be 4.37 first, and the SI units is going to be meters cubed. We're also given gravity, 9.81 meters per second squared, this being a meter per second squared being the SI units. And right off the rip, we can gather enough information that the buoyancy force is going to equal the combination weight of the ice and the bear, right? And we can make an equation out of that, being FB equals weight of the ice plus the bear. And this is a very important equation that we're going to be using, right? The buoyant force is, so this is going to be the equation of the combined weight of ice and the bear. The buoyant force is, well, I'll just write it right here. The buoyant force is, the force of buoyancy is equal to density of water, density of water, Vg, volume and gravity, times volume times gravity. And the weight of ice is going to, so this is the buoyancy force. The weight of the ice is going to be the weight of ice is equal to the density of the ice, the density of the ice times volume and the gravity. And since we know both of those, and the buoyancy force equals a combination of both of these, we're going to need to combine them. So the weight of the bear in this situation is going to be density of water times volume times gravity minus the density of the ice, times the volume and the gravity. And since they both have Vg in the situation, we can just factor it out real quick, make it easier. So weight of the bear is equal to, density of the water minus density of the ice, and we have the volume and the gravity on the outside here. So what we do for here is we just plug in, because we have this equation now. So when we plug in, we want to do W bear is equal to the density of the water, which was given here, 1025, minus density of the ice, which we were given, 917, times the volume, which is 4.37, times the gravity, which is 9.81. And the final the final answer we get here is going to be 4,629.6 newtons. We check here, it was rounded up, so We'll round up 4,630 newtons of force. This is the final answer. This is the weight of the heaviest bear that this ice can support without sinking completely beneath the water. And those are going to be my two questions for week 7B homework.